Last time, we built addition out of switches. That AND gate you wired up turned out to be a few transistors. But look what we called those things. And, or, not. English words borrowed for a job that isn't English. That's the trap. You already speak this language, so you assume you know what the gates mean. Here's a sentence for you. If 9 is a prime number, then the moon is made of cheese. 9 isn't prime. The moon isn't cheese. Both halves false, unrelated. That sentence is true. Not a joke, not a loophole, true, by the rule that makes your AND gate work. I'm not going to justify that yet. Sit with it. It should feel wrong, and that feeling is the lesson. Let's go back further than the gates. Take an expression with holes in it, placeholders, x or x1. That's a statement form, and it has no truth value yet. It's got slots. Drop statements into the slots, and you get a statement back. Or drop in the truth values. Try one yourself. The form is x and, or x. For x, take 3 is less than 7, true. For a 9 is prime, false. Inside, false or true, so true. Then true and true. So z is true. Now watch what your hands just did. You never thought about primes or 5, you pushed 2 values around. So let's write the connectives down as operations on those 2 values. Negation. Z is not x. If x is false, z is true. If x is true, z is false. Conjunction. Z is x1 and x2. 4 rows, 2 slots each holding one of 2 values. False, false, false. False, true, false. True, false, false. True, true, true. Only that last row survives. Disjunction. Z is x1 or x2. Now only the first row is false. 1 true input is enough. Nowhere in that AND table did anything ask what x1 means. There's no slot for meaning, which raises something worth chasing. 2 inputs give you 4 rows, and each row you fill with true or false. So how many 2-input connectives could there be? Count the ways you can fill that column. 3rd century B.C. A school of philosophers in Megara are arguing about the word if. One of them is Philon, and he proposes something almost dismissive. The conditional is true when it does not begin with something true and end with something false. That's the whole criterion, one forbidden combination, every other case fine. Notice what he's given up. He fixes the truth of the whole thing using only the values of the parts. Not whether the first has anything to do with the second, not whether one causes the other. Relevance is nowhere, which is strange to say about if. That's the word we use for consequences. All right, let's build his table. Z is x1 implies x2. Row 1, false and false. Does it begin with something true? No. So it's true. 2, false, true. Still doesn't begin true, so true again. 3, true, false. Begins true, ends false, the forbidden one, z is false. Last one, true and true. Ends true, so it's fine and z is true. 3 rows true, 1 row false. That's your implication, complete. Now back to the moon. 9 is a prime number, false. So you're in one of the top 2 rows, and in both, z is true. The cheese never mattered. Put anything you like there, the table stopped caring once the first half came out false. 2 more while we're here. Antivalence, your XOR gate, true exactly when the inputs disagree. And equivalence, the XNOR gate. Z is x1 if and only if x2, true when they agree. Build this one yourself before we move, not x1 or x2. 4 rows. Write out the column, then tell me which table you've just written. Philon had a teacher. Diodorus Cronus, same school, and he wanted something stronger. For Diodorus, a conditional had to hold always. Not just happen to have acceptable values in front of you. which is closer to what you mean when you say if, and it's the objection you're still holding. The quarrel got loud. A line survives joking that even the crows on the rooftops were cawing about conditionals. Philon's rule is the one we kept. Not because he convinced anyone, because his version can be settled by two values, and Diodorus can't. That doesn't answer Diodorus. Relevance is what the table throws away, and it's gone. So what can the table see? Which assignments make an expression come out true, and that's enough to rebuild your hardware. The set of all assignments of the variables for which z becomes true is the satisfaction set of z. A of z. If that set contains every possible assignment, if you can't make z false, z is universally valid. A tautology. And two expressions with the same satisfaction set are equivalent. Let's work one. Three variables. z1 is x1 or x3, z2 is x2 implies not x3, z is z1 and z2. 8 rows now, 3 slots, 2 values each. Start at all false and count up with me. All false, z1 is false, so z is false. Same for false, true, false. Take false, false, true. z1 is true, x2 is false, the implication holds z is true. But false, true, true kills it. x2 true, x3 true, so not x3 is false, true implies false. Keep going and you land on 4 triples that work. That's E of z. Now the one you built yourself. Not x1 or x2, and x1 implies x2, same satisfaction set. As far as logic is concerned, those aren't two expressions that agree. They're the same expression. Careful with these two symbols. The if and only if combines truth values, the way plus combines numbers. 4 plus 9 is 13. Equivalence transforms formulas. The way a plus b squared becomes a squared plus 2, a b plus b squared. Statements about statements. 3 tautologies before we go on. X or not x, the excluded middle. Not x and not x, a contradiction can't hold. And this one. If x1 implies x2, and x1 is true, then x2. Which of those do you use every day unnamed? Here's where it pays. Take not x1 and x2. De Morgan says that's not x1 or not x2. Check the rows with me. False, false, the and is false, so the left side is true. On the right, true or true. Only the last row makes the and true, so only there does the left go false. On the right, false or false. Same column. The other one runs the same way. Not x1 or x2 is not x1 and not x2. Read that second one as a wiring diagram and something falls out. An OR gate is an AND gate with all 3 wires inverted. 2 inputs flipped in, output flipped out. Same satisfaction set. So nothing downstream can tell which one you built. One more, the shape of every argument you've ever made. If x1 implies x2, and x2 implies x3, then x1 implies x3. Say x1 is your sensor reading over 80 degrees, x2 is the fan switching on, x3 is the current rising. You know the first link from the wiring, the second from the motor. The third you never checked, the chain hands it to you. Philon lost the argument about relevance to his teacher. 2,000 years later, he won it on silicon. Your gate never knew what any of it meant. That's exactly why you can swap it.